class 11th chemistry unit 6 thermodynamics, and in this video we are going to discuss about second law of thermodynamics, third law of thermodynamics, and Gibbs energy change and equilibrium. First come to entropy and second law of thermodynamics. Actually this second law of thermodynamics is related to the entropy, and there are number of forms in which second law can be stated like this. Entropy is the loss of energy available to do work. Another form of second law of thermodynamics states that the total entropy of a system either increases or remains constant, it never decreases. Next one is entropy is zero in a reversible process. It increases in an irreversible process. Entropy of any isolated system always increases. In exothermic reactions, heat released by the reaction increases the disorder of the surroundings, and overall entropy change is positive, which makes the reaction spontaneous. These are the different forms of second law of thermodynamics. Now, absolute entropy and third law of thermodynamics. The entropy of any pure crystalline substance approaches zero as the temperature approaches absolute zero. This is called third law of thermodynamics. Absolute zero means 0 Kelvin. Okay. The importance of the third law is that absolute values of entropy of pure substances can be determined. Again, remember friends, we have discussed that absolute value of internal energy and absolute value of enthalpy cannot be determined, but absolute value of entropy can be determined using this third law of thermodynamics. Clear? Now, Gibbs energy change and equilibrium. Reversible chemical reaction is the reaction which can proceed in either direction simultaneously. What does it mean? It means that reactants convert into products and products convert into reactants at the same rate, so that a dynamic equilibrium is set up. Okay. What is this equilibrium and what is this dynamic equilibrium? We will discuss in the next chapter. Okay, this means that the reactions in both the directions should proceed with a decrease in free energy, which seems impossible. Clear? Which seems impossible. It is possible only if at equilibrium the free energy of the system is minimum. Clear? Free energy of the system is minimum. So the criterion for equilibrium for this reaction, that is A plus B converting into C plus D, is that this free energy change is zero. This is the criterion for equilibrium. That at equilibrium change in free energy is zero. Gibbs energy change for a reaction in which all reactants and products are in standard state is known as standard Gibbs energy change, represented by this symbol. It is related to the equilibrium constant of the reaction as follows. That is, delta G of reaction is equal to standard Gibbs energy of reaction plus RT ln K. R is a gas constant, T is the temperature. This ln represents the natural logarithm. Again, dear friends, there is a separate topic of logarithm. Okay, and this K represents the equilibrium constant. As we discussed, at equilibrium, change in Gibbs energy is equal to zero. That's why this relationship can be written like this. That is, standard Gibbs energy of a reaction is equal to minus RT ln K. Yeah? Now, this is a natural log. If this natural log is converted into the basis of 10, then this ln is replaced by log, log. Okay, and this whole term is multiplied by 2.303, and we will get this. Standard Gibbs energy change of a reaction is equal to minus 2.303 RT log K. Remember this relationship between standard Gibbs energy and equilibrium constant. Okay, and we already discussed that this Gibbs energy change is equal to enthalpy minus T delta S, and this is equal to minus 2.303 RT log K. For strongly endothermic reactions, what are endothermic reactions? Reactions in which heat is absorbed. This standard enthalpy of reaction is large and positive. That's why if we correlate with this, we can say value of equilibrium constant is very less than 1, and the reaction is unlikely to form much product. On the other hand, in case of exothermic reactions, this standard enthalpy change of reaction is large and negative, and this standard Gibbs energy is also large and negative, and this equilibrium constant is greater than 1, hence reaction can go to near completion. Okay, simply we can say for spontaneous change delta G is negative and K is greater than 1. Okay, and for endothermic reaction where enthalpy change is positive, K is less than 1 and unlikely to form much product. Okay, now see some questions. Calculate standard Gibbs energy for reaction for conversion of oxygen to ozone. This is the reaction. 3 by 2 O2 gas converting into O3 gas at 298 Kelvin. If Kp for this conversion is 2.47 into 10 to the power minus 29. Okay, simply K is given, we have to find out delta G standard, and as we know relationship is this is standard Gibbs energy change of a reaction is equal to minus 2.303 RT log Kp, and R is gas constant 8.314 joule per Kelvin per mole, and Kp is given. Put the value in the formula, we'll get this one. Delta G standard is equal to minus 2.303 multiplied by 8.314, and temperature is 298 Kelvin, and log of this is the value of Kp. Let's just solve it. Now question arises, how we solve this log? Dear student, there is my separate video regarding this, how to solve log and anti-log. Okay, you can watch it. Then if we solve it, we will get this one. This is in joule per mole. If you convert into the kilojoule, this will be 163 kilojoule per mole. One more question. Find out the value of equilibrium constant for the following reaction at 298 Kelvin. And reaction is 2NH3 gas plus CO2 gas converting into NH2CO, NH2 aqueous plus H2O liquid, and standard Gibbs energy change at the given temperature is minus 13.6 kilojoule per mole. Now use this formula. Delta G standard is equal to minus 2.303 RT log K. We have to find out the value of K. That's why I rearrange this equation. Log K is equal to minus delta G standard divided by 2.303 RT. Now in this question, delta G is given in kilojoule per mole and value of R is joule Kelvin per mole. That's why convert this into joule by multiplying 10 to the power 3. Okay, for the another values, this is 2.303, 8.314 joule per Kelvin per mole. This is the temperature, and if we solve, we will get 2.38. But this 2.38 is the value of log K. If we want to find out the value of K, then we have to take the anti-log of this 2.38. That's why K is equal to anti-log of 2.38, and if we solve this anti-log, we will get 2.4 into 10 to the power 2. Okay. Now again, how to solve this log and anti-log? Watch my, there is one separate video. Okay. Thank you. Now this chapter is over, and in the next video I will start the new chapter, equilibrium.